Hello everyone, I am Anshu Gupta, and today I'm going to describe about our tool DP-HLS, which is a high-level synthesis framework for accelerating dynamic programming algorithms in bioinformatics. Now let's start with a brief introduction and motivation behind our work. In the field of bioinformatics, there are multiple applications which uses sequence alignments, be it whole genome assembly to assemble short reads, or multiple sequence alignments used in phylogenetics, or in comparative genomics to compare multiple genomic data together, or if you want to align two signals used in base calling, or if you want to do RNA structure analysis. All of these algorithms use a sequence alignment, and they have one thing in common, that is they all use dynamic programming as their main underlying algorithm. So now let's understand what is dynamic programming and what is 2D dynamic programming specifically used in sequence alignments. So let's start with an example where we need to compare these two sequences. So what will we do? We will take two input sequences, name it as query and reference, and then place it along the rows and the columns of a DP matrix. And then we will perform these three different steps as illustrated over here. So in the initialization step, we will initialize the first row and the first column of the DP matrix. The second step is scoring, where we will fill each of the cells of this DP matrix using recurrence equations. And in the final step, we will perform traceback, where we will try to find the optimal path of the alignment depending on the optimal scores. And then at the end, we will get the final output. So this algorithm is first introduced by Needleman-Wunsch for aligning two genomic sequences. And since then, we see multiple variations of these algorithms used in multiple fields of bioinformatics. So let's start with understanding what are the variations and how can they be categorized. So we'll start with each of the categories one by one. So one category of variation can be caused due to differences in the input sequences which you want to align, be it like DNA sequence or RNA sequence or complex number sequences. The second set of initialization can be caused, variation can be caused due to initialization values differences. Global, linear, semi-global, what kind of alignments you want to see, all of them are associated with different initialization scores. Another category of variation can be caused due to differences in the scoring functions or the recurrence equations through which we will fill each of the cells of the matrix. And these recurrence equations varies with different types of penalties you want to use. Another set of variation can be caused by differences in the traceback strategy. So the overall traceback strategy is same, but they differs regarding the starting and the ending points, as we can see over here, for different applications. And that's how we come up with these 15 different kernels. And each of these kernels are used by multiple highly cited tools used in bioinformatics for multiple applications, be similarity search, accurate similarity search, or whole genome alignments, and so on. And all of these kernels are generated by modifying the initial Needleman-Wunsch version of the algorithm based on the categories mentioned in the previous slides. Now, this 2D algorithm is computationally expensive because it grows quadratically with the sequence lengths. And hence, there has been a lot of work to accelerate these algorithms on specialized hardware such as ASICs and FPGAs. Now, let's understand how DP algorithm maps to the hardware. So this DP algorithmic computation can be performed using waveform parallelism, where we can see each of the antidiagonals have scores, which is computed in parallel with each of the P's. And each of the P's are arranged linearly, where the reference sequences are being streamed in systolically, and it is being mapped as a linear systolic array architecture in the hardware. And each of the wavefronts are computed in a pipeline fashion. And we see this systolic array architecture to accelerate DP algorithms in multiple tools and multiple works, which are listed over here. They all provide great speedups, but there's one disadvantage to it, that is they mostly are non-configurable. That means they don't support newer applications. And if you want to configure them to support newer applications, you need to redesign things from scratch, which can take months. So high-level synthesis addresses this issue to some extent. So high-level synthesis provides an automated design process where it allows user to provide the design constraints in higher abstraction level language, such as in C, C++, and those specified constraints are mapped automatically to the optimal hardware design by the HLS tool. And that's how HLS tools increases the productivity of the hardware design process a lot. And user does not need to redesign manually using RTL from scratch. But there's one disadvantage to it. That is, if you want to generate optimal hardware design, whose performance can be comparable to the RTL approaches, we need to provide optimal design constraints in the form of pragma directives. If the optimal pragma directives are not provided, mostly the design process done by HLS is non-synthesizable and it's non-optimal. So this also requires some sort of hardware understanding. With this, our objective of this work is to generate a generic framework which can accelerate 2D DP algorithms and which is highly programmable and can be used in multiple applications. And we want to create efficient hardware design in very simple steps without involving any hardware design expertise, and thus improving the productivity to a great extent. And keeping these objectives in mind, we created DP-HLS, which is a generic framework. It's highly programmable, supports multiple applications, and it creates a hardware design in very simple steps without requiring any hardware knowledge by the user, and it improves the productivity. So this DP-HLS framework is divided into two parts, front end and the back end, where front end consists of highly customizable C++ based APIs, where user can provide their design constraint in form of the parameters. And then the back end converts all these customizations from the front end to its optimal hardware architecture using predefined HLS directives. And once this hardware architecture is designed by the HLS tool, it is then deployed to the FPGA. So let's understand how the DP-HLS works. So the first step is to specify the kernel configurations or the design constraint by the user, and then the kernel will be simulated. This is all done by the front-end part of the DP-HLS. Then we perform the synthesis and the co-simulation, and user can analyze the final implementation results, which is done by the YTS-HLS tool. And then once the final implementation is done, it generates the bit stream and is finally deployed to the FPGA. Now let's understand the front-end architecture of the DP-HLS. So the first level of customization is providing your own initialization rows and column scores, which differs from application to applications. So here we have provided two applications, a global alignment and local alignment, and their scores. Similarly, for your own requirement, you can provide your own initial rows and column score by just modifying few lines of code instead of redoing multiple lines of code and redesigning things from scratch. The next set of customization is providing your own sequence alphabet, whether you want to align DNA sequence or RNA sequence or complex number sequences, how many scoring layers should be there, what should be the scoring parameters used in the recurrence equations, what should be the maximum number of sequence lengths, and what should be the starting and ending points of traceback pointers and their states. The third set of customization is user can provide their own P function, that is the recurrence equation performed by each of the P's in the systolic arrays. Now here we have provided two examples for the linear and affine gap penalty. And for different types of gap penalties, there can be different recurrence equations, but all of those recurrence equations can be provided in just a few lines of code in the DP-HLS framework. Another set of customization can be provided by the user as traceback strategies. So there can be different traceback strategies for different applications. And each of these traceback strategies can be realized as finite state machine, where it can have different states and different starting and ending points. And for all of them, we just need to add few lines of code as mentioned over here. This is an example for the global linear alignment. And similarly, just few changes required, and then you can have a new traceback strategy for new application. And then DP-HLS also supports multiple levels of parallelism, which can be controlled by the user. So here, one kernel block depicts one systolic array architecture, which aligns one pair of input sequences. Similarly, DP-HLS allows the deployment of multiple kernel blocks, which is mapped to multiple parallel systolic array architectures, aligning multiple pairs of sequences in parallel. And this is not supported for just one type of homogeneous kernel. There can be multiple heterogeneous kernels, each of the kernel having its own number of blocks to be deployed in FPGA in parallel. And all of those levels of parallelism can be controlled by these parameters NB, NK, and NPE. NP basically providing the number of processing elements to be there in one linear systolic array. So that's how DP-HLS supports interloop and outer loop parallelism, which is all customizable by the user.
Now, let me introduce the DP-HLS backend. First, let's take a look from the algorithm perspective, so we can have an idea of the dependencies and the bandwidth requirements of computing the wavefront. In this example, the numbers on the left is a segment of the zeroth column score, and the numbers above it is the last row score of the previous chunk. The sequence on the left is a segment of query, and sequence above it is the reference sequence. Currently, we are computing the score of the green wavefront. It depends on the yellow and brown wavefronts. We're explicitly highlighting the dependency wavefronts and the current wavefront on the right-hand side. Each PE is mapped to a score in the wavefront, and since different element is at different row, so each PE is computing the score of a row. Only a segment of the query is needed to load for this chunk, but they need to be parallelly accessible by each individual PE at the same time. Additionally, each wavefront depends on a segment of the input reference sequence, and each element in this segment is mapped to a PE as well, so each of the nucleotide bases of this segment need to be parallelly accessible by the PEs. However, only the first PE would read from the previous chunk's score. The segment of a local reference sequence is like a sliding window and is updated with a new symbol from the reference sequence for each wavefront. Now, let's move to the next wavefront, which is the light blue color. The value in the local reference is updated, and it loads a new symbol from the reference. And also the score of the light blue wavefront is calculated based on the new wavefront dependencies, which is the brown wavefront and the green wavefront, which we just computed. Similarly, as we move to the purple wavefronts, the local reference is updated again, and the score is computed based on the blue and green wavefronts. The previous illustration will give a natural way to map each element to hardware. This is a detailed graph showing the connection between the storage device and the computing units. In this graph, the purple components are the computing logic. It includes the PEs for the scoring equations, also the maximum finding logic, and also the traceback logic. It also has several buffers. The white blocks represents the buffers implemented in registers or shift registers, and the gray buffers are implemented in the DRAM. The local query buffer, the local reference buffer stores the query and reference dependency of the wavefront. As we just mentioned, each PE need to be able to access each of the query bases and reference bases at the same time. So they are implemented in an array of registers. But the local reference buffer is a shift register. This is achieved by breaking down the array completely using the HLS array partition pragma. And the Vitesse HLS tool can automatically determine the shifting logic of the shift register. DP memory stores the input scores of the previous two wavefronts as dependencies, and the output score buffer takes the output score from each PE. Obviously, each individual element in those two buffers need to be accessed by the PEs at the same time as well, so they are partitioned completely, just like the local query and local reference. Then an on-row pragma is used to create multiple instances of the processing elements to form a systolic array. There is also a previous row score buffer to handle the inter-chunk dependencies. The score of the first row of the current chunk depends on the score of the last row of the previous chunk. So the last PE will write its score to this buffer, and the first PE will read scores from this buffer. At each cycle, only one score is read to this buffer, and only one score is read from this buffer. So a single BRAM is enough to implement it. Also, the address to read is always ahead of the address to write. so it won't cause any dependency issue. Additionally, each PE keeps its local maximum scores and updates them based on the score it computes. Then they are sent to a reduction maximum finding logic to find the overall optimum score. They are also used to track the traceback starting index. The maximum finding logic can be easily changed to minimum finding logic depends on the algorithm needs. Optionally, there could be an array of BRAMs to store the output traceback pointer. After iterating the square matrix, the traceback logic reads from those traceback BRAMs to compute the final traceback. Then I want to show some results of our framework. First, we want to show the evidence that the systolic array is being generated through the HLS. Since it is hard to inspect the semantics of HLS generated RTL design, we can infer this from the scaling behavior. So these two figures is the throughput scaling for the global linear kernel and dynamic time warping kernel. The green line is the scaling with respect to the number of parallel blocks in the kernel, and the blue line is the scaling with respect to number of PEs in the systolic array. And the scaling with respect to number of blocks, it perfectly exhibits the block level parallelism and this slightly saturating scaling with the number of PEs, it demonstrates the underlying systolic array. Similarly, all types of resource of the two kernels scales as expected with the number of PEs and blocks as specified in the design. Also, the throughput of DP-HLS generated kernel is similar to the three baseline kernels which were built with the RTL designs. And the resource utilizations is it's comparable to those baselines. Comparing to the CPU baselines, our kernel achieves 1.3 to 32 times speed up, and comparing to the GPU kernels, we have 1.4 to 17 times speed up. We also have an HLS baseline comparison to the Smith-Merleman kernel from the Vitis Genomics library. And the HLS baseline in the genomics library is implemented very differently from our kernel. And we can see that resource utilization is, its resource utilization is smaller than ours, but our kernel completes the task with smaller cycle counts, so it achieves a little bit higher overall throughput.
In summary, we present DP-HLS, a high-level synthesis-based framework to design hardware accelerators for dynamic programming-based bioinformatic algorithms. In particular, the user doesn't need to have any hardware design background to customize any of the hardware kernels. It is highly scalable, and the results we have shown are stable in terms of throughput and resource utilization scaling. In addition, the throughput and resource utilization are all comparable to accelerators with RTL designs. Finally, we achieve a maximum of 17 to 32 times iso-cost speedup compared to CPU and GPU baselines respectively, making this tool highly efficient. We would like to acknowledge our Professor Yatish Tarakia from UCSD, as well as collaborators from the AMD-omics group. We have released an archive preprint shown by this QR code, as well as the GitHub repository for our code shown here at this QR code. Thank you so much.